Space is quiet in a way nothing on Earth can imitate. A silence so deep it presses against you. A silence broken only by the faint hum of distant starlight and the slow drift of dust across the dark. For a century, we believed we understood the scale of the place we call home. We believed the Milky Way was a galaxy of modest size, a clean spiral stretching 100,000 light-years across. Textbooks drew its shape with confidence. Every diagram showed the same familiar outline. Every classroom repeated the same number. But space does not care about our certainties. New instruments, sharper eyes, and deeper surveys began whispering the truth. A truth that did not match the maps. A truth that peeled away the comfort of familiar diagrams. The galaxy seemed wrong. Measurements disagreed. Stars moved too fast. Streams of torn galaxies drifted in places where nothing should have been. And at the farthest edges, light behaved as if pulled by something enormous, something unseen, something stretching far beyond the limits we drew. The revelation arrived quietly, a slow accumulation of contradictions, a pattern forming in the darkness. And then, the James Webb Space Telescope looked outward. Its infrared vision pierced dust clouds that blinded every previous generation. It traced stellar streams farther than imagined. It measured the bending of distant light with impossible precision, and in the glow of that data, the Milky Way unfolded into something larger, something older, something far more monumental than the numbers carved into our textbooks. The galaxy was not 100,000 light-years wide. It was at least twice that, maybe more. It was a giant, hiding behind its own light. The story of how we uncovered the true size begins not with triumph, but with confusion. For decades, astronomers could only guess at the galaxy's edge by measuring where bright stars faded into the dark. It was a crude tool born of limitation. From inside the spiral arms, every direction looks crowded. Dust blocks the view. Gas hides the core. We watch the galaxy from the worst possible vantage point, buried within it. Imagine standing in the center of a vast city. Lights, towers, walls of steel rising on every side. You cannot see the outer streets. You cannot glimpse the horizon. All you know is what surrounds you. That was humanity trying to measure its own galaxy. The first hint came from motion. Stars near the edge moved too quickly. Their speeds defied expectations. According to visible mass, they should have escaped into intergalactic space. They should have drifted away like dust in the solar wind. Instead, they stayed, bound by something invisible, something massive, something extending farther than the brightest stars. Then came hydrogen maps. Radio waves traced clouds stretching into the darkness, far beyond the traditional border. Then came tidal streams, ribbons of stars from devoured galaxies wrapping around us like cosmic scars, reaching distances that shattered the old models. Each piece of evidence pointed to the same conclusion. The Milky Way did not end where we thought it did. The visible disk was only the center of a structure far bigger, far heavier, far older. A shadow of the true galaxy. Imagine watching a flock of birds circling in the sky. Their path reveals the unseen wind. Stellar streams behave the same way. They orbit the Milky Way like ancient fossils drifting through time, their paths shaped only by gravity. When scientists tracked these streams, they saw them stretching into regions we once labeled empty. Their trajectories only made sense if the galaxy extended outward by another 100,000 light-years or more. The universe was correcting us. And then, James Webb confirmed it. Its vision pierced the fog. It saw the faint glow of stars on the far side of the galactic disk. Stars invisible to optical telescopes. It measured the slight warping of light from distant galaxies as it passed through the Milky Way's gravitational field. That warping revealed mass, and that mass revealed size. A galaxy far heavier than expected. A galaxy whose dark matter halo stretched so wide, it blurred into intergalactic space. The Milky Way was not small, it was a titan. Suddenly, everything changed. Models of the Andromeda collision shifted, the timeline tightened, the search for life expanded, the number of stars doubled, the number of planets soared. The very idea of where the galaxy ends dissolved into uncertainty. Our cosmic neighborhood had been misdrawn for generations, and the implications reached far beyond our spiral arms. If we mismeasured our own galaxy, the one we live inside, the one we observe every night, then how many other galaxies were underestimated? How many spirals across the universe were larger, heavier, older than recorded? What else about the cosmos had we misunderstood simply because our tools were too weak, our vantage point too limited, our imagination too small? This story is not just about size. It is about perspective, about the danger of believing we understand the universe when we stand on one small rock, orbiting one average star, buried in one corner of a galaxy so large it hides more than it reveals. James Webb did not just expose the true scale of the Milky Way. It exposed how little we truly know. And the deeper we look, the more the darkness pushes back, revealing a galaxy still unfolding beyond the boundaries we once trusted. The map has been redrawn, but the journey has barely begun. Monty, the journey to uncover the Milky Way's true size did not begin with advanced telescopes or billion-dollar observatories. It began with a simple question that refused to disappear. Why did the edges of our galaxy behave like nothing we understood? Why did stars at the boundary move as if pulled by a force far beyond the visible disk? Why did gravitational models break the moment they tried to describe the outskirts of our home? For years, scientists tried to fit the data into the old map. They adjusted values, refined equations, recalculated mass. But no matter how carefully they worked, the numbers refused to obey. The outer regions of the galaxy acted like a place with more gravity than anyone expected, as if something hidden stretched far into the darkness. The first real clues came from motion. Space, though silent, is full of movement. Every star drifts, every cluster orbits, every stream flows across the gravitational landscape carved by the Milky Way. When astronomers tracked these motions with better precision, they discovered a strange pattern. Stars far from the center moved with speeds that seemed impossible. They slid through the halo as if riding an invisible current. Their paths curved around something much larger than the visible disk. It was like watching boats sweep around a coastline you could not see. The Gaia spacecraft sharpened this picture. With measurements of over 1 billion stars, it produced the most detailed motion map of the galaxy ever created. It revealed subtle curves, faint arcs, and delicate streams stretching like ghostly trails across the sky. These were the remnants of devoured galaxies, fossils drifting through the halo. Their orbits made no sense unless the Milky Way was larger, heavier, and more expansive than any model predicted. As the motion data piled up, the old boundary at 100,000 light-years collapsed. The galaxy's influence clearly extended much farther. But how far? That was still unknown. The next breakthrough came from hydrogen. Hydrogen clouds are among the faintest, oldest, and most widespread objects in the galaxy. They drift through the halo in long filaments, nearly invisible to optical telescopes, but radio waves can see them. Massive dishes scanned the sky, mapping where hydrogen gathered. The results were unexpected. Clouds appeared at distances no one anticipated, regions that, according to the old diagrams, should lie beyond the Milky Way's reach. The galaxy's footprint extended outward, like a shadow stretching across the void. Still, the picture was incomplete. Hydrogen revealed structure, but not boundaries. Stars revealed motion, but not mass. To understand the true scale of the galaxy, astronomers needed a tool that could measure the invisible, something that could map gravity itself. That tool arrived with the James Webb Space Telescope. Webb's infrared sensors opened windows into the hidden galaxy. Through dust, through gas, through the thickest regions of the disk, it saw stars once lost to sight. It mapped the far side of the galaxy from within the spiral arms. And then it did something even more important. It watched how light from distant galaxies bent as it passed near the Milky Way. This bending, gravitational lensing, reveals the mass of whatever it passes through. When scientists examined the lensing patterns, they found distortions larger than expected. The galaxy exerted more gravitational pull than its visible mass could explain. Webb exposed the invisible structure surrounding us, the massive dark matter halo, a sphere of unseen particles extending hundreds of thousands of light years beyond the bright core. The galaxy was no longer a clean spiral. It was an island of stars wrapped in a colossal cloud of dark matter. A structure so diffuse that no telescope could see it directly, yet so massive that it shaped everything around it. The discovery shifted our understanding of the Milky Way from a tidy picture into a sprawling giant, a galaxy twice as wide, a region twice as deep. A structure that blends gradually into intergalactic space. As the new measurements took shape, everything else began to shift. Satellites once thought distant were now revealed to orbit within the halo. Streams once thought to drift through empty space were shown to trace the galaxy's outermost regions. Even the timeline of our future changed. Andromeda's approach, long predicted to begin in 4.5 billion years, now seemed poised to start earlier. The gravitational reach of both galaxies extended farther than believed. Their halos might already be brushing against each other, beginning an encounter long before the visible disks meet. The more the data improved, the clearer the story became. The edge of the Milky Way was never a sharp line. It was a gradient, a slow fading from density to emptiness. A transition too subtle for earlier generations to detect. And in that fading darkness, new discoveries waited. The outer halo, once thought barren, turned out to be rich with ancient stars, red dwarfs drifting alone, streams from devoured galaxies sweeping across enormous arcs. Tidal remnants looping around the disk, these stars formed a bridge between the known galaxy and the unseen territory beyond it. Every new observation stretched the boundary farther. 120,000 light years, 150,000, 180,000, 200,000, 250,000. The numbers rose with each new measurement, each new calculation, each new instrument aimed at the darkness. The story of the Milky Way's true size was no longer a quiet correction to a textbook. It became a transformation of perspective. A reminder that even the galaxy we call home is still unfolding before us, still surprising us, still revealing that the universe is larger, older, and more mysterious than our maps allow. The exploration had begun again, but the journey ahead would reveal more than size. It would reveal the history of the galaxy itself. A history written in stars torn apart. A history hidden in streams circling the void. A history waiting in the darkness beyond the old edge. And that history was about to come into view. The deeper astronomers explored the outskirts of the Milky Way, the stranger the picture became. The galaxy was no longer a clean spiral with a sharp border. It was a layered structure, each layer revealing something new about its size, its past, and its hidden forces. And among the most important clues were the stellar streams, those long, graceful rivers of stars stretching across the sky. At first glance, these streams seemed delicate, thin threads of light curving through space. But their story was far from gentle. Each stream carried the memory of a galaxy the Milky Way had consumed. These were the remnants of systems torn apart over millions of years, evidence of ancient mergers frozen in motion. Stellar streams became the rulers that measured the unseen. Because stars in these streams do not lie. They orbit according to gravity alone. They drift along paths shaped only by the total mass of the Milky Way. And when those paths extended farther than the supposed edge, it meant the galaxy's pull extended farther too. One of the first streams to reveal this was the Sagittarius stream. It wrapped around the Milky Way like a ribbon. Vast, elegant, unmistakable. Earlier surveys mapped only fragments of it. Webb and Gaia mapped its full arc. a band of stars looping hundreds of thousands of light-years through the halo. Its orbit made no sense under the old model. It was too wide, too stretched, too far. The galaxy had to be bigger, much bigger. Then came GD1, a thin and fragile line of ancient stars drifting through the outer halo. Its curvature exposed something even more extraordinary. It bent as if pulled by a mass we could not see, a mass too distant to belong to the visible galaxy. This bend forced astronomers to expand their models. The only way the orbit worked was if dark matter extended much farther than previously believed. The galaxy's true boundary moved outward again. More streams appeared as surveys deepened. Long arcs, broken strands, disrupted trails. Some were so faint they blended almost perfectly into the background. Others traced loops so vast they crossed through what we once assumed was empty intergalactic space. But the stars did not travel through emptiness. They traveled through the Milky Way's real gravitational domain, an invisible empire far wider than the bright disk at its center. With each discovery, the galaxy expanded. 100,000 light-years had become 150, then 180, then 200, then more. The streams revealed a galaxy that did not end where the light faded. A galaxy defined not by its brightness, but by its reach. The next layer of evidence came from dark matter, the galaxy's invisible backbone. A halo of unseen particles extending outward in every direction. Dark matter does not glow. It does not reflect. It does not absorb. It does not leave a trace except through gravity. But its influence is everywhere. It holds the galaxy together. It shapes its rotation. It binds the stars in orbits that defy visible mass. For decades, dark matter models struggled to fit the Milky Way. The inner regions behaved predictably, but the outer halo refused to follow simple curves. Too much mass seemed to exist at vast distances. Measurements did not match expectations. Then Webb measured the bending of distant light, gravitational lensing at a scale never achieved before. Light passing through the Milky Way curved far more than a 100,000 light-year galaxy could cause. The only explanation was an enormous halo of dark matter, stretching much farther than thought, a hidden sphere of gravity millions of times more massive than all the visible stars combined. The galaxy's shape transformed from a flat disk into a deep, layered structure, a bright core of stars, a swirling disk of spiral arms, a thick halo of ancient clusters, and beyond that, a vast cloud of dark matter, fading slowly, blending into the cosmic web. The visible part was only the center, a lighthouse within a sea of shadow. As the new models took shape, scientists realized that the true size of the Milky Way could not be defined by light alone. It had to be defined by gravity, by where the galaxy's influence ended, and gravity extended far beyond the regions telescopes once traced. The streams confirmed it. The halo upheld it, and the mass calculations demanded it. For the first time, the Milky Way's true dimensions began to emerge, wider than believed, heavier than imagined, deeper than any textbook allowed. Yet the implications reached even farther. A larger galaxy meant a shorter distance to Andromeda in terms of gravitational influence. The two giants, long thought comfortably separated, were now close enough that their halos may already be touching. If true, the collision, once predicted to begin billions of years from now, had effectively already started, unseen in the darkness where their halos overlap. A larger galaxy meant more stars, more planets, more potential worlds for life. The census of the Milky Way expanded by hundreds of billions. The number of habitable zones multiplied. The galaxy grew crowded in ways that challenged our imagination. And a larger galaxy meant new questions. If we had misjudged our own home, how many other galaxies were underestimated? How many spirals across the universe were twice as wide, twice as massive, twice as full of stars as we thought? The error was not a local mistake, it was a universal one. The Milky Way was the first domino, and the others were already falling. But beneath all these revelations lay a deeper truth. The size was not just about numbers. It was about history. Every stellar stream, every dark trail, every faint star drifting in the halo told a story of galaxies swallowed, collisions survived, structures reshaped. The Milky Way had grown through violence, through mergers, through the slow tearing apart of smaller galaxies, through the accumulation of matter across billions of years. And the next chapter of that history was still unfolding in the darkness beyond the old edge. A chapter the telescopes were only beginning to glimpse. As the map of the Milky Way expanded, something else changed, something more subtle, more unsettling. The structure of the galaxy began to reveal contradictions that no old model could explain. The outer halo behaved strangely. The spiral arms appeared incomplete. The rotation pattern refused to align with expectations. The deeper astronomers looked, the more the galaxy resembled a puzzle assembled from fragments of other worlds. And the fragments carried their own stories. For decades, astronomers assumed the Milky Way's spiral arms were clean, symmetrical, well-formed structures. Elegant curves tracing the disk like ripples from a stone dropped in water. Textbooks showed 4 clear arms, each labeled and neatly drawn. But when infrared instruments and star motion maps peeled back the dust, the arms twisted into something far more complex. In some regions they branched. In others they faded. In others still, they doubled back or formed strange, broken paths. The arms behaved like the memory of collisions long past, distorted remnants of ancient mergers hidden beneath the glow of newer stars. Instead of a perfect spiral, the galaxy was a mosaic, a layered tapestry of structures built over billions of years. The first sign of this complexity came from the far side of the disk, a region invisible to optical telescopes. Webb revealed an arm stretching where none was expected, an entire structure hiding behind walls of dust, a ghost arm, thousands of light years long. Its existence meant one thing: the galaxy had far more structure than previously believed. More arms, more branches, more features carved by time and gravity. Some arms were thick and bright, others were faint, composed of ancient stars drifting in loose formation. A few extended so far into the halo that astronomers debated whether they were true arms or the stretched remains of devoured galaxies. The idea that the Milky Way was orderly began to fade. The galaxy was a living system, constantly evolving, constantly reshaped by the cosmic forces acting upon it. The next revelation came from motion. Stars in different regions of the arms moved at different speeds. Some sped ahead, others lagged behind. The arms themselves were not rigid structures. They were patterns, density waves, temporary gatherings of stars that drift through the disk, like traffic jams along a cosmic highway. A star might join an arm, travel within it for a time, then leave it behind. This created a paradox. If the arms were only waves, how did they remain coherent for billions of years? Why didn't they dissolve into chaos? The answer lay in the galaxy's mass. A larger galaxy supported stronger gravitational patterns. The arms persisted because the Milky Way was far heavier than assumed. Its dense halo and expanded disk stabilized the waves, holding them in shape over cosmic time. The revelation was profound. The galaxy's size was not just a matter of distance. It was the reason the structure survived at all. Then came the anomalies, stars that refused to obey the expected rotation curve. Some moved too fast, some too slow, some drifted with the precision of a clock. Others meandered unpredictably through the halo. Each anomaly hinted at a different history, a different origin, a different galactic merger hidden somewhere in the past. Streams from ancient galaxies left scars. Collisions tilted orbits. Tides pulled stars into new paths. Entire groups of stars moved in harmony, their shared motion revealing their shared birth in galaxies long consumed. The Milky Way was not a single civilization. It was an archive, a collection of stellar cultures gathered through billions of years of cosmic conquest. Every orbit held a story. Every velocity carried a memory. Every stream traced a wound. As these patterns emerged, astronomers began reconstructing the galaxy's past. Ancient mergers rose to the surface like fossils uncovered by careful excavation. One event stood out among them, a collision so massive it reshaped the entire structure. Gaia and Enceladus. This ancient galaxy collided with the Milky Way around 10 billion years ago. It was not a small dwarf, it was large, heavy, powerful. The impact threw stars into chaotic orbits. It created the thick disk. It seeded the halo with billions of foreign stars. It even changed the Milky Way's rotation. A single merger had altered the destiny of our galaxy. But Gaia and Enceladus was not alone. Other collisions followed over billions of years. Smaller galaxies added their mass. Larger ones nudged the Milky Way's orbit. Streams from these mergers still drift through the halo, each one a fossil in the sky. This violent history explained the galaxy's strange shape, the unexpected arms, the uneven rotation, the tilted orbits, the faint structures seen in infrared light. The Milky Way was not a quiet spiral. It was a survivor of endless cosmic battles, rebuilt again and again through the destruction of others. Yet even with these revelations, questions remained. The structure beyond the 200,000 light-year mark was still uncertain. The halo faded into darkness with no clear boundary. Streams stretched farther than expected, and the dark matter halo extended even beyond that, reaching into distances too vast to define with confidence. The outer galaxy remained a frontier, a region shaped by forces we still struggle to understand. And as the map expanded, so did the implications. A galaxy twice as large means twice the influence, twice the gravitational pull, twice the depth of cosmic history. The Milky Way no longer felt like a single, unified object. It felt like an entire domain, an enormous gravitational kingdom that gathered matter from across millions of light years. And as the story of its structure came into focus, another revelation waited at the edges of the halo. A revelation that would change how we understand our future. As the shape of the Milky Way grew clearer, the next question emerged like a rising tide. If the galaxy was larger, heavier, and more complex than anyone believed, what did that mean for its stability? What did it mean for its future? And what did it mean for our place inside it? The crisis point began not with the galaxy's structure, but with its motion. Rotation is the heartbeat of a spiral galaxy. Every star, every cluster, every cloud of gas orbits the center. These orbits should follow a simple rule. Objects farther out should move more slowly. Gravity weakens with distance. The pull fades. The motion should relax into gentle curves. But the Milky Way defied this rule. In the outer regions, stars moved too fast. Their velocities pushed the limits of what the galaxy's visible mass could hold. Some stars skimmed the edge of escape speed, moving so quickly they should have flown into intergalactic space long ago. Yet they remained, locked in place by a force we could not see. At first, this was a mystery, then a warning, then a revelation. The speeds were not random. They formed a pattern, a signature of something far more massive than the bright disk, something shaping the galaxy from the shadows, something controlling the motion of stars, thousands of light years from the center. Dark matter. The crisis began when models tried to explain these speeds. The visible galaxy was too small, far too small, to generate the observed pull. With every fast-moving star, the old map became more impossible to defend. The Milky Way could not be 100,000 light-years wide. It had to be bigger, much bigger. The halo of dark matter surrounding it had to be enormous. extending far beyond the visible boundaries. When new models expanded the galaxy's size to 200,000 light-years, the rotation curves finally made sense. The impossible speeds were no longer impossible. The fast-moving stars were no longer anomalies. The outer halo was no longer empty. The galaxy's weight had been miscalculated. Now the numbers fit. But the crisis was not over. Because some stars still moved too fast. Even with the expanded halo, their speeds hovered just below escape velocity. It was a delicate balance, so precise it seemed unnatural. As if these stars were the survivors of violent events, carrying momentum from ancient collisions. These were the high-velocity halo stars. Faint, distant, scattered across the outskirts like sparks drifting from a dying fire. Their speeds told a story the galaxy had spent billions of years trying to hide. They were remnants of cosmic violence. Some had been launched during mergers with ancient galaxies. Some escaped from regions near the central black hole. Some were survivors of close encounters with clusters or dense star systems. Each star carried a history written into its velocity. Webb and Gaia tracked them with unprecedented precision. Their paths revealed something astonishing. Many of the fastest halo stars traced orbits aligned with known stellar streams. They were survivors of torn galaxies thrown outward during the final stages of mergers. Others drifted in nearly straight lines through the halo, as if punched into motion by events powerful enough to reshape entire systems. But the most disturbing stars were those that moved almost, but not quite, fast enough to leave the galaxy. They hovered at the threshold, barely bound. Locked in a fragile grip, held by the outermost regions of the dark matter halo. These stars traced the boundary of the Milky Way. Not the visible boundary. Not the textbook boundary. The true boundary, where gravity thins into the void. Their existence forced astronomers to confront a question that echoed across every field of galactic science. How big is the Milky Way really? If these stars were bound, the galaxy extended farther. If they were unbound, the halo was lighter than predicted. Every velocity measurement shifted the frontier outward or inward. Every orbit redrew the map. And then, the crisis deepened. Because once the galaxy doubled in size, every calculation built on the old measurement crumbled. The timeline of the Andromeda collision shifted. Estimates of star population doubled, the number of planets expanded, even our models of dark matter distribution changed. The universe suddenly felt heavier. The revision forced astronomers to re-examine everything. Distances, mass, age, structure, future. Size affects all of them. The Milky Way's expansion was not a small correction, it was a seismic shift in perspective. A recalibration of our understanding of cosmic architecture. And the crisis reached its peak when simulations began to reveal what a galaxy of this size truly meant. A larger Milky Way meant stronger gravity. Stronger gravity meant earlier interactions with neighbors. Earlier interactions meant a faster timeline for cosmic events, long thought distant. The collision with Andromeda, once predicted to begin in 4.5 billion years, appeared sooner, perhaps 4 billion, perhaps less. And the first signs of interaction might already be unfolding in the dark matter halos surrounding both galaxies. The crisis point was no longer theoretical. It was real. Present. Immediate in cosmic time. The Milky Way had outgrown its old image. It was larger, more powerful, and more influential than anyone believed. And its future was racing toward us with gravitational force. But the crisis held one more revelation, one that would redefine not just the shape of the galaxy, but its entire history as a living, evolving structure. A revelation waiting in the violent past of the Milky Way. To understand the true size of the Milky Way, scientists had to travel backward, not through space, but through time. Because a galaxy is not born large, it grows. It evolves. It consumes. And the Milky Way's past revealed a truth far more violent than anyone imagined. The modern galaxy, the elegant spiral sketched in textbooks, is only the latest version of a structure continually rebuilt through destruction. To map its true extent, scientists had to uncover the history of every collision, every merger, every ancient scar carved into its halo. The first clues came from stellar streams. They wrapped around the galaxy like ghostly fingerprints, each one the remnant of a small galaxy torn apart long ago. They traced long, looping orbits, ribbons of stars stretched thin across the sky, faint, distant, and ancient. These streams were cosmic archaeology, relics of events billions of years old. Gaia's motion data, combined with Webb's infrared clarity, revealed that many of these streams orbited far beyond the edge of the visible disk. Far beyond where any textbook map placed the boundary, they extended into the deep outskirts, moving through regions previously assumed empty. These streams were not just features. They were rulers, measuring tools, marking where the galaxy's gravitational influence ended. The farther out the streams went, the larger the galaxy became. And the streams went far. Some circled 100,000 light-years from the core. Some reached 150. Some approached 200,000. A few pushed even farther, tracing paths in regions once considered intergalactic space. Each discovery expanded the map. Each new measurement forced the boundary outward. But the streams did more than redraw the galaxy. They revealed the story of how the Milky Way grew. Because every stream came from a meal. The Milky Way is a survivor built from the ruins of others. The Gaia-Enceladus merger. The Kraken collision. The Helmi streams. The Sequoia dwarf. The Sagittarius dwarf. Still being devoured today. Each one added stars. Each one added mass. Each one extended the galaxy's reach. The more scientists studied these disrupted remnants, the clearer the picture became. The Milky Way was not always this size. Its growth was not slow and gentle. It was explosive, chaotic, driven by catastrophic mergers. The largest mergers left scars so deep they still shape our motion today. Chemical signatures revealed stars that formed in older galaxies with different element ratios. Kinematic data showed populations of stars orbiting on strange, tilted paths, evidence of ancient collisions that shattered the early Milky Way and rebuilt it layer by layer. The halo, a vast sphere surrounding the disk, was almost entirely made of these remnants. Ancient stars with eccentric orbits, drifting through darkness far from the bustling spiral arms. They were fossils of destroyed galaxies, still carrying the motion and composition of their original homes. But something unexpected emerged in the data. The biggest mergers were not ancient history. They continued into more recent cosmic epochs. The Milky Way was still growing, still consuming, still evolving, still expanding through accretion. This was not a static galaxy frozen in time. It was alive, changing, reshaping itself with every dwarf galaxy that wandered too close. As scientists mapped more streams, they uncovered a pattern. The most distant streams, the ones orbiting near the edge of the halo, did not belong to a single ancient merger. They came from many. A dozen or more small galaxies had been torn apart across billions of years, each adding new stars to the outskirts. These additions thickened the halo. They extended the gravitational field. They pushed the Milky Way's influence farther into space. And then the realization struck. The galaxy was not simply larger than expected. Its growth explained the size. The Milky Way is not a neat spiral. It is a composite structure, a patchwork of debris, layers of history stacked upon one another. Its outer regions were a graveyard of past collisions. Its shape was sculpted by the physics of accretion. Its boundaries blurred because they were constantly shifting. Every merger expanded the halo. Every stream mapped new territory. Every torn satellite pushed the edge outward. The galaxy's size was not fixed. It was the result of billions of years of gravitational conquest. And this understanding introduced a deeper revelation. If the Milky Way grew through mergers, and if those mergers left stars scattered across the outskirts, then the galaxy must contain far more mass than visible. The halo was not empty. It was populated by billions of ancient stars too faint to detect with earlier surveys. Their presence added weight. Their motions altered calculations. Their distribution revealed the true extent of the galaxy. What began as a measurement problem became a historical one. To understand the Milky Way, scientists had to understand every galaxy it had swallowed. And one by one, the victims emerged from the data. A giant merger 10 billion years ago that reshaped the Milky Way's disk. Another, slightly smaller, that tilted the halo and altered its rotation. Dozens of tiny dwarfs integrated into the outer regions. Hundreds of globular clusters captured and dispersed. The galaxy's true size was written not in light, but in motion, in the orbits of stars born in other galaxies. The past created the present. The present defined the map, and the map kept growing. This was the revelation. The Milky Way is not a single galaxy. It is the accumulated remains of many, a gravitational empire built from conquered neighbors. To measure it is to measure every collision in its history. To map it is to map the aftershocks of a billion-year war. And as new telescopes revealed more victims, the size of the empire continued to expand. The Milky Way was not just bigger than imagined. It was built to become bigger. If the Milky Way's violent past revealed why the galaxy grew so large, the next revelation explained how we measured it so wrong for so long. For decades, astronomers relied on light, visible light, to map the disk, the arms, the core, and the surrounding halo. But light deceives, light hides. Light reaches only where dust, gas, and density allow. To truly understand the galaxy, scientists needed motion, not brightness. Velocity, not visibility. Gravity, not glow. And that realization changed everything. The breakthrough came with the Gaia spacecraft, a satellite orbiting the Sun, quietly measuring the position and motion of over 1 billion stars with microscopic precision. Gaia did not care whether a star was bright or dim, distant or near, ancient or newborn. It tracked them all. Every shift, every wobble, every subtle drift across the sky. Gaia turned the Milky Way into a dynamic map, a galaxy not of pictures but of orbits. With Gaia's motion data and Webb's deep imaging combined, a new portrait emerged, one that revealed the galaxy not as a static disk, but as a swirling, complex gravitational system extending far beyond the visible stars. The first shock came when astronomers plotted the rotation curve. As expected, stars in the inner regions followed familiar patterns, fast near the center, gradually slowing outward. But beyond a certain distance, the slowing stopped. The speeds flattened. Stars far from the center moved just as fast as stars much closer in. This was impossible unless the galaxy held far more mass than visible matter accounted for. Dark matter explained the curve, but the curve also explained the size. To keep stars moving at those speeds, 130 kilometers per second, 150, sometimes even 200, the Milky Way needed a gravitational field extending deep into the outskirts. The halo had to be massive, wide, and densely populated. The galaxy's boundary had been underestimated because the gravitational effects did not stop at the edge of the visible disk. Gravity ignored the textbook diagrams. Gravity continued, pulling far into the darkness. This alone doubled the estimated size, but motion revealed even more. Because once Gaia mapped 1 billion stars, patterns emerged. Patterns impossible to see before. There were stars drifting in elongated orbits stretching far into the halo. There were clusters looping in wide arcs around the galaxy. There were streams cutting across space like cosmic highways. Some of these objects traveled through regions once believed empty. Their presence rewrote the map. Their motions marked the true extent of the Milky Way's reach. Gaia revealed the invisible skeleton of the galaxy. Not made of stars, not made of dust, but made of gravity. And with that skeleton traced, the galaxy grew. 100,000 light years. 150,000. 200,000. Perhaps even more. Every motion pushed the boundary outward. But motion revealed something else, something stranger. The galaxy's structure was not shaped from within, but from without. Satellite galaxies, dwarfs orbiting far beyond the disk, moved through space in paths that traced the Milky Way's total mass. The Large Magellanic Cloud, the Small Magellanic Cloud, the Sagittarius Dwarf, Draco, Ursa Minor, each one moved as if held tightly by something huge. Their orbits were too stable for a smaller galaxy. Their speeds were too high for the traditional measurements. The satellites were not independent neighbors. They were captives, bound, controlled by a gravitational field larger than any astronomer had once admitted. Their motion revealed the true size of the empire. But the biggest surprise came from the outskirts, from the region where the galaxy's gravity thins into the void. Here, Gaia revealed stars drifting at the edge of escape velocity. These stars moved so fast that a slight change in the galaxy's mass would free them entirely. They were balancing on a cosmic knife edge. If the galaxy were smaller, as old models claimed, these stars would have escaped long ago. The fact that they stayed meant the halo was larger than predicted. Their orbits extended the boundary outward once more. Motion kept pushing the edge. Gravity kept redrawing the map. The galaxy kept expanding, not physically but conceptually, into the space once called nothingness. As scientists traced more motions, a final realization emerged. The Milky Way is not a disk with a halo. It is not a flat spiral floating in space. It is a gravitational sphere, a vast, diffuse, multi-dimensional structure extending far beyond the thin glowing disk where most stars reside. The visible galaxy is just the core. The rest is a shape defined by gravity, not light. A soft-edged, uneven, expanding boundary. A sphere of influence, not a solid object. A region, not a structure. This meant the Milky Way had no outer wall, no border, no clean end. It fades. It thins. It dissolves into darkness. Motion revealed the truth. The galaxy is not measured by where stars stop glowing, but by where gravity stops winning. And gravity still wins far beyond the disk. The Gaia-Webb partnership formed the foundation of a new measurement era. A galaxy seen not by sight, but by force. Size became not a distance, but a domain. Not an edge, but a reach. Not a picture, but an influence. The Milky Way was not just bigger. It was something fundamentally different than the diagram suggested. A colossal, invisible architecture. A gravitational continent with no shoreline. A system so vast that even light could not reveal it alone. Motion told the truth. Gravity showed the shape, and the shape was enormous. The motion of stars revealed the shape of the Milky Way. But motion alone could not explain why so many stars moved at impossible speeds, near the edge of escape, yet still held inside the galaxy's vast gravitational reach. To understand that mystery, astronomers had to look deeper into the invisible structure surrounding us. Not the glowing disk, not the spiral arms, but the dark envelope, the halo that contains more mass than every star combined. It is in this darkness that the true scale of the Milky Way became undeniable. Dark matter forms the galaxy's unseen frame. a spherical cloud of invisible particles that stretches outward in all directions. No light reflects from it. No instrument sees it directly. But gravity exposes it everywhere. Stars at the outer edge travel too fast to be held by visible mass. Hydrogen clouds move in patterns that normal matter cannot explain. Satellite galaxies orbit at distances so extreme they should drift away. Something powerful binds them. Something vast. Something silent. Dark matter. It does not shine, but it shapes everything. For decades, astronomers treated the dark matter halo as an afterthought, a mathematical correction, a hidden mass that balanced equations. But with Gaia, Webb, and radio surveys combined, the halo emerged as the dominant structure of the Milky Way. The stars were the decoration, the halo was the foundation, and the foundation extended far beyond old estimates. Earlier models placed the halo's edge near 100,000 light-years. Later models pushed it to 150,000. But new data revealed something unprecedented. The halo expanded to at least 200,000 light-years, perhaps 250,000. Some models suggested 400,000 or more. A few extreme scenarios even hinted at 1,000,000 light-years. 1,000,000. Half the distance to Andromeda. The Milky Way was no longer a single galaxy. It was a sphere of gravitational control stretching deep into space. A silent empire carved from darkness. The discovery reshaped cosmic maps instantly. The space once considered between galaxies was no longer empty. It was contested territory, regions where halos overlapped, where gravity pulled from multiple directions, where the very definition of galactic boundaries blurred. The edge of the Milky Way became not a line, but a gradient, where density slowly faded, where influence tapered, where nothing ended sharply. The halo proved this beyond doubt. As astronomers traced the motions of outer stars, a pattern emerged. These stars moved as if floating through a vast, uneven cloud. They drifted through a landscape of invisible mass, shaped by lumps and clumps formed over billions of years. The halo was not smooth. It was textured, rippled, filled with scars from ancient galactic collisions. Every merger left its imprint. Rivers of dark matter stretched thin, knots compressed by tidal forces, waves and arcs born from gravitational shock. The invisible became a shifting terrain, a silent record of every violent moment in the galaxy's history. And the stars revealed this map with their motion. Some sped up as they passed through denser regions of dark matter. Others slowed slightly in softer zones. Streams warped as invisible weight tugged on their paths. Satellite galaxies curved in arcs shaped by the unseen. The halo became a living structure, not a static cloud. It expanded and contracted subtly over cosmic timescales. It responded to mergers. It influenced orbits. It shaped the galaxy from the outside inward. And it kept revealing new layers. Infrared observations showed faint, distant stars sprinkled throughout the outer halo, ancient survivors from devoured galaxies. Their presence marked the true boundaries of gravitational influence. These stars were too far, too dim, too scattered to belong to the visible disk. But they still moved with the Milky Way. They drifted in slow arcs, circling the core from enormous distances. They were the final evidence that the galaxy's size extended far beyond what light alone revealed. Because if these stars were still bound, still orbiting, still held by the Milky Way's pull, then the halo had to reach them. And if the halo reached them, the galaxy was enormous. But the revelation did not end there. Dark matter also shaped the future, specifically the approaching collision with Andromeda. The timelines once calculated used smaller halo estimates. But larger halos meant earlier interaction, not through stars, not through gas, but through gravity. If both halos stretched hundreds of thousands of light years, they were already touching. If they touched, the collision had begun. Silently. Unseen. In the dark. Two invisible spheres interpenetrating across the gulf of space, gravity already linking them, tidal forces already nudging stars. The first stage of a cosmic merger already underway. The realization shifted every prediction, every timeline, every model. The collision no longer belonged to a distant future. It belonged to now, invisible, slow, but inevitable. Dark matter did not just double the galaxy's size. It accelerated its fate. But the halo also revealed something more profound. The Milky Way, despite containing billions of stars, was built almost entirely from the unseen. 90% of its mass was dark matter. 10% was everything else: stars, planets, gas, dust, black holes, nebula, clusters, everything humans could detect. We lived inside an invisible colossus, a gravitational sculpture stretching through space. A structure so massive it shaped the motion of galaxies around us. Dark matter was not a feature of the Milky Way. It was the Milky Way. Without it, the galaxy would unravel. The arms would disperse. The disk would dissolve. The stars would drift into intergalactic space. Light revealed the surface of a cosmic iceberg. Motion revealed the mountain beneath. And that mountain extended farther, deeper, wider than any earlier measurement had admitted. The halo was the true boundary, the true shape, the true size. A sphere of influence stretching hundreds of thousands of light years. And with this understanding came the most humbling truth of all. We do not live inside a galaxy of stars. We live inside a galaxy of darkness, holding the stars in place. An invisible universe within the visible one. A structure that defines everything we see. A presence that surrounds us completely. Silent, massive, endless. The revelations about dark matter reshaped the Milky Way. But nothing transformed our understanding more than counting what filled it. Not the halos. Not the streams. Not the satellites. The stars. For decades, estimates placed the Milky Way's population near 200 billion. A number large enough to feel infinite, yet small enough to fit in equations. A number repeated in textbooks, documentaries, planetarium domes. But it was wrong. Once the galaxy's true size doubled, the star count followed. Not by a little, by an entire order of magnitude. Because doubling the radius does not simply double the volume. It expands it by 8. 8 times more space. 8 times more room for stars of every kind. 8 times more possibilities. And the galaxy filled that room. The Milky Way held not 200 billion stars, but closer to 400 billion. Perhaps more. Perhaps far more. The truth is that the faintest stars hide in the darkness. Tiny red dwarfs that shine so dimly they vanish beyond a few hundred light years, let alone hundreds of thousands. They are the silent majority. 70% of all stars, invisible in most wavelengths, flooding the galaxy with their mass, their planets, their quiet presence. The galaxy was not emptier than we thought. It was overflowing, and the implications rippled outward instantly. 400 billion stars meant 400 billion chances for planets. Hundreds of billions of worlds drifting through a spiral giant. Worlds warm, frozen, storm-covered, ocean-coated, molten, barren, or thriving. Even a conservative estimate suggested that the majority of stars hosted planets. Not some, most. The Kepler Space Telescope proved this years ago. Planetary systems were common, not rare. Planets formed naturally, easily, inevitably. They were the byproduct of star formation, not exceptions. With the new star count, the Milky Way suddenly held at least 250 billion planets. A number too large to picture. A number that rewrote the search for life. Because among those planets was a smaller subset, worlds within the habitable zone. Planets with the right temperature, the right sunlight, the right distance from their stars to allow liquid water. Even if only 1% qualified, that left millions of habitable worlds. Millions. Once, the idea of life beyond Earth belonged to guesswork. Now it belonged to probability, statistical inevitability, mathematical consequence. The galaxy's new size sharpened the paradox lurking in every mind. If there were millions of chances for life, if the cosmos overflowed with worlds, if complexity had billions of opportunities to arise, why was everything silent? Why, across 400 billion stars, had no signal reached us? Why no contact? Why no message? Why no evidence of another intelligence? The Milky Way grew larger. The silence grew louder. Yet the expansion of our star count did not just deepen the mystery, it reshaped the timeline of the galaxy itself. With more stars came more energy, more explosions, more mergers, more stellar births and deaths. The galaxy's history became more dynamic, more violent, more crowded. Every star had lived a life of its own. Everyone had formed in a collapsing cloud, burned for billions of years, and died in brilliant explosions or quiet fades. Every heavy element, iron, carbon, oxygen, had been forged in those deaths. Every planet, every moon, every drop of water owed its existence to generations of stars long gone. Once, humans looked up and thought they lived in a quiet corner of the galaxy, a modest neighborhood, an average spiral, a thin disk surrounded by darkness. Now they saw the truth. The Milky Way was a metropolis, a crowded, swirling, luminous continent of stars stretched across 200,000 light years. A place alive with energy, movement, and evolution. But the new star count revealed something deeper, something hidden in the halo. Not bright stars, not warm giants, but ancient remnants, stellar fossils, white dwarfs, neutron stars, black holes, objects left behind after billions of years of stellar life cycles, silent witnesses to cosmic history. Their presence in the outer halo revealed that the Milky Way was born from generations of mergers and collisions. Those remnants were older than the disk, older than the arms, older than much of the galaxy's present structure. They were survivors from ancient galaxies consumed long before the Milky Way became the giant it is today. And they continued to drift, cold and near invisible, marking the outskirts of a structure larger than any astronomer had pictured. The more scientists counted, the more they realized the galaxy's population was not just vast, it was layered, structured, shaped by billions of years of evolution. Inner disk stars, young, bright, rich with metals. Halo stars, ancient, sparse, born in distant galaxies. Stream stars, ripped from collisions, orbiting in long arcs like threads of forgotten history. Core stars, dense, powerful, spiraling around the supermassive center. All measured, all counted, all part of the growing picture. 400 billion stars, 400 billion stories, 400 billion histories woven into a single gravitational tapestry. And the number kept climbing. With every new survey, every deeper exposure, every faint signature, more stars appeared. More distant, more ancient, more numerous than imagined. The Milky Way no longer resembled a tidy diagram. It resembled an ocean, vast, crowded, filled with currents and tides, shaped by unseen forces. An ocean so large that no single instrument could map it completely. An ocean whose true population might never be known. Yet even incomplete, the new count revealed the most humbling truth of all. The galaxy is overflowing with possibilities. overflowing with worlds, overflowing with places where life could begin, overflowing with environments where evolution could take root. And as the numbers grew, humanity's place in the galaxy became smaller, not in importance, but in scale. One star among 400 billion. One world among billions. One civilization on the edge of a vast, ancient spiral. The Milky Way did not shrink humanity's place. It magnified the wonder of existence. Because in a galaxy this large, the miracle is not that life might be rare. The miracle is that we exist at all. The story of the Milky Way's true size unfolds like a slow awakening. A shift in perspective so profound that it reshapes everything, from the science of galaxies to the place humanity occupies within them. This is the journey ahead. A journey through light and darkness, motion and silence, revelation and mystery. It begins with the map we thought we understood. A tiny spiral, a familiar diagram, a textbook image repeated across generations. A galaxy measured at 100,000 light-years wide, neatly contained, comfortably finite. Then the instruments sharpen. Dust parts. Infrared light pierces the obscured regions. Stellar motions reveal invisible forces sculpting everything around us. Measurements swell outward. Boundaries dissolve. The galaxy stretches far beyond human expectation. The preview ahead explores this transformation step by step, how the discovery began, what data forced a revision, and how a centuries-old understanding unraveled under the weight of new evidence. The story traces the clues that pointed toward a larger Milky Way long before any telescope confirmed it. Stars moving too fast at the edges, gas clouds drifting in patterns that defied simple explanations, satellite galaxies following orbits too stable for a smaller gravitational field. It follows the instruments that exposed the truth. The Gaia spacecraft, mapping 1 billion stars with impossible precision. Infrared observatories peeling back the dust layers, exposing structures hidden for lifetimes. Radio telescopes tracing hydrogen far into the halo. And finally, the James Webb Space Telescope, seeing deeper into the galaxy's heart and outskirts than any instrument before it. These tools transform the Milky Way from a flat disk into a complex, three-dimensional realm, a structure not bounded by light, but by gravity. A system where the visible spiral is only the luminous core of an enormous gravitational domain stretching hundreds of thousands of light-years in every direction. The preview reveals how that domain formed through ancient mergers, violent collisions, and slow assimilation. Rivers of stars torn from smaller galaxies. Tidal streams wrapping around the core like cosmic scars. Star clusters drifting through the halo as fossils of forgotten worlds. Piece by piece, the galaxy's true architecture emerges. The story ahead also explores how this larger size reshapes cosmic timelines. How the approaching Andromeda galaxy interacts with the Milky Way's expanded halo. How the collision begins not with visible contact, but with the merging of dark matter envelopes far beyond the reach of ordinary telescopes. How gravitational tides shape the future of both galaxies millions of years before the first stars ever brush past one another. The preview continues with the implications for life. 400 billion stars means billions of planets in zones warm enough for liquid water. A galaxy overflowing with opportunities for biology, evolution, and perhaps intelligence. A cosmic arena where the question, "Are we alone?" becomes not philosophical but statistical. The search grows wider. The possibilities grow deeper. The silence grows stranger. And the narrative widens further still. Every galaxy in the universe faces the same revision. The same underestimation. The same hidden mass. The same invisible scaffolding of dark matter shaping everything from spiral arms to cosmic expansion. The Milky Way is not an exception. It is a template. The preview offers a glimpse of how recalibrating our galaxy demands recalibrating the universe itself. Distance measurements shift. Mass estimates change. dark energy calculations wobble under new gravitational baselines. The cosmic web becomes denser, more connected, more dynamic. This journey leads to the outskirts, where the galaxy fades into intergalactic darkness. The place where star density drops to almost nothing. Where lone stars drift through regions once thought empty. Where the halo dissipates quietly into the void. Here the idea of a boundary becomes an illusion. A human attempt to draw a line on a structure that refuses to be confined. The story ends by confronting the mystery that remains. Not what the Milky Way is today, but how much more of it waits to be discovered. How many stars hide beyond current detection limits? How many unseen streams still orbit the core? How many measurements future observatories will rewrite? The preview ahead is not a conclusion, it is an invitation. An invitation to witness a galaxy unfolding in real time, its true size emerging through layers of light and darkness. An invitation to stand at the edge of understanding and look outward into a structure so vast it defies imagination. A galaxy not of 100,000 light-years, but 200,000 or more. A galaxy defined not by what shines, but by what pulls. A galaxy alive with motion, history, and invisible forces. The story that follows is the story of how we measured home incorrectly for 70 years, and how the cosmos corrected us. The galaxy we live in hides more secrets than any map can capture. Its structure stretches beyond diagrams, beyond numbers, beyond what the human mind evolved to understand. Yet in its darkness lie details so remarkable that each one reshapes how we see our place in the cosmos. One of the most striking truths is how little of the Milky Way we can actually see. Even with modern telescopes, the human viewpoint is trapped inside a spiral arm, buried beneath layers of dust, surrounded by brightness and shadow. Only about 10% of the galaxy is visible in ordinary light. The rest lies concealed, reachable only through infrared, radio waves, and the slow motion of stars drifting through space. The darkness is not empty, it is simply hidden. Another remarkable fact lies in the chemical history of the galaxy. Every atom of iron in human blood was forged in a star that lived and died long before the sun existed. The calcium in bones, the oxygen in lungs, the carbon in every living cell, all born from ancient explosions scattered across the galaxy's vast regions. The Milky Way is not just a home. It is an ancestor, a silent creator shaping every element of life through cosmic fire. Deep inside the galaxy's core, a supermassive black hole sits at the center of countless orbits. Not a monster consuming everything around it, but a quiet anchor holding the inner regions in place. Even from 26,000 light-years away, its gravity influences the sun's slow path around the galaxy. The core may be hidden behind dust and gas, but its presence shapes every motion, every orbit, every star. It is the heart of a system too large for its own light to reveal. The spiral arms tell their own story. They look permanent in diagrams, frozen like paint on a canvas, but they are not fixed at all. They are waves of density, moving slowly around the galaxy, gathering gas and releasing it, creating stars for a brief cosmic moment before passing onward. The sun drifts through these arms over millions of years, entering and leaving regions of enhanced star formation. The arms are not roads. They are tides rising and falling across a galactic sea. Even the space between stars holds mysteries. The interstellar medium is not a vacuum, but a thin ocean of gas and dust drifting between orbits. Supernova explosions send shockwaves through this medium, sculpting bubbles that stretch thousands of light-years, carving cavities where new stars eventually form. These bubbles collide, merge, and reshape the galaxy's internal landscape. The Milky Way breathes through these expanding shells, each one the echo of a star's final light. At the outer edges, the halo contains relics of ancient galaxies long lost to time. Some stars there formed before the Milky Way itself existed, carried into its gravitational field by collisions that predate human history by billions of years. Their low metal content reveals their age. Their strange orbits reveal their origin. They are wanderers, survivors of forgotten worlds, proof that our galaxy is a mosaic built from many lives, not just one. Another surprising truth lies in the galaxy's motion. The Milky Way is not stationary in space. It moves through the universe at hundreds of kilometers per second, pulled by the gravity of nearby clusters, drawn along the cosmic web. The galaxy falls toward a vast gravitational anomaly known as the Great Attractor, a region so massive that entire clusters drift toward it silently. Even as the Milky Way spins, it travels, carried across a universe alive with movement. Gravity binds galaxies, but light reveals their past. When astronomers study distant galaxies billions of light years away, they are looking back in time, seeing the universe as it once was. Those early galaxies appear smaller, brighter, more chaotic, evidence that collisions and mergers shaped everything we see today. The Milky Way carries those ancient patterns within its halo, memories etched into motion and mass. Even the sun's journey through the galaxy carries hidden stories. It completes one full orbit every 230 million years. That means, since Earth formed, the sun has circled the galaxy fewer than 30 times. Every rotation places humanity into a new region of space, a new neighborhood of stars, a new environment shaped by tides of matter and radiation. Life on Earth has evolved while the solar system drifts along this ancient path, unaware of the cosmic dance unfolding around it. Far beyond the sun's orbit, the outer halo hides a reservoir of unseen stars. Some drift for billions of years, never approaching the disk again. Others circle in wide arcs, completing orbits so large that an entire species could rise and fall before they return to their starting point. The halo stretches so far that time itself feels different there, slow, distant, unbound by the rhythm of the bright inner galaxy. Even the emptiness between galaxies is not truly empty. Thin gas, rogue stars, lost planets, and dark matter swirl in the intergalactic medium. Every galaxy swims through this unseen ocean, leaving faint trails behind, creating ripples that propagate for millions of years. The Milky Way has such a wake, evidence of its motion across the cosmic landscape, faint but measurable. The size of the galaxy is not a static number. It changes with every new instrument, every new model, every new satellite discovered at the edge of detection. What seems empty today may reveal structure tomorrow. Boundaries that appear sharp soften under deeper surveys. Distances that once felt final shift outward with every improvement in resolution. These truths form the quiet foundation of the story. A reminder that the galaxy is not simply larger than believed. It is deeper, older, more complex, more layered. A place shaped by collisions, enriched by starlight, sculpted by gravity, held together by darkness. A place where every star contributes to a larger narrative. A place where every orbit carries history. A place where light and shadow weave the structure of home. The Milky Way is not merely wide. It is profound. Not merely massive, but ancient. Not merely bright, but filled with mysteries waiting to be revealed. And every fact uncovered brings us closer to understanding the vast and silent architecture that surrounds us. The story of the Milky Way's true size ends not with a measurement, but with a perspective. A shift in how we see ourselves, our home, and the universe that surrounds us. For generations, humanity believed it understood the shape of its galaxy. 100,000 light years across, a graceful spiral drifting in the dark. A familiar diagram drawn in every classroom, trusted in every book. But the galaxy was never that simple. The deeper we looked, the more the darkness revealed. The spiral arms hid fragments of ancient worlds. The halo held stars older than the Milky Way itself. The outskirts merged seamlessly with the invisible domain of dark matter. Motion carved boundaries no telescope could see. Gravity stretched far beyond the reach of light. The map we carried was not wrong out of ignorance. It was limited by vision, limited by tools, limited by the vantage point of a species observing the cosmos from a single star wrapped inside a dense spiral arm. Only with new instruments did the galaxy open itself. Only with deeper measurements did its true structure emerge. A structure wider, heavier, older, more layered than the first astronomers could ever imagine. A galaxy not of 100,000 light-years, but 200,000 or more. A galaxy whose halo blends into intergalactic darkness. A galaxy defined not by brightness, but by gravitational reach. A galaxy shaped by billions of years of collisions, filled with the remnants of devoured systems. A galaxy overflowing with stars, hundreds of billions, each with worlds of their own. A galaxy moving through space like a drifting continent, carrying all life on Earth with it. The revelations changed our place in that structure. They made the sun feel smaller, the Earth more fragile, the night sky deeper. Yet they also made existence more extraordinary. Because even in a system this large, this ancient, this violent, life emerged on a tiny blue world orbiting an ordinary star. Life rose while galaxies collided. Civilizations blossomed while tidal streams wrapped around the halo. Humanity learned to look upward while the galaxy slowly shaped itself through gravity's quiet work. The Milky Way is not static. It is not fixed. It is not done growing. It evolves with every passing million years. It consumes new material, forms new stars, creates new worlds. It spins and drifts and breathes in cosmic time. And through all of that, humanity exists in one fleeting moment, brief, delicate, but profoundly meaningful. Every discovery about the galaxy's size deepens a truth older than science. The universe is not built for human convenience. Its scale dwarfs imagination. Its history stretches far beyond memory. Its forces move with slow, unstoppable rhythm. Yet within that immensity, humanity continues to understand, to question, to measure, to reach, to build instruments that see farther, to expand knowledge, to illuminate what once lived in darkness. It is in that pursuit, quiet, persistent, curious, that our place gains meaning. Because the galaxy does not shrink when we learn more about it. It expands, not in size, but in wonder, in depth, in the feeling it leaves inside the human mind. The Milky Way is not a distant object. It is our home. A home so vast that countless civilizations could rise and fall without ever knowing each other existed. A home where stars live and die in cycles that forge every element of life. A home drifting slowly toward its future, shaped by forces beyond sight, carrying humanity along with its motion. In the end, the most profound revelation is not the number, not 200,000 light-years, not 400 billion stars, not the halo of unseen matter, but the realization that we live inside something still unfolding. A galaxy alive in every direction. A galaxy that will continue to change long after its current shape fades. A galaxy whose story humanity has only just begun to read. The night sky above Earth is not a static dome. It is a window into a living structure, a vast, ancient, ever-evolving realm where every star is part of a larger story. A story written across time. A story measured not by boundaries but by the reach of gravity and the persistence of light. The Milky Way is bigger than believed, older than expected, more complex than imagined, and in its immensity lies the greatest reminder of all. Humanity is small in size, but infinite in curiosity. And it is curiosity that turns darkness into understanding. The galaxy surrounds us with silence, depth, and mystery. But within that silence, humanity finds purpose. To explore, to discover, to question, to continue the journey through a universe that grows more astonishing with every new measurement. And as long as humanity keeps looking up, the story of the Milky Way will never be finished. If this story moved you, don't forget to like, share, and subscribe to Space Facts, where we explore the universe through the eyes of those brave enough to venture into the unknown. The cosmos is vast, but every story matters. See you among the stars. The revelations about the Milky Way's true scale do more than redraw a map. They reshape the context of everything humanity has ever observed. Because a galaxy twice as wide is not simply a larger home, it is a different stage upon which the history of the cosmos unfolds. The first shift appears in the age of the galaxy itself. For decades, astronomers believed the Milky Way formed from a calm collapse of primordial gas. A gentle coalescence, slow and steady, yielding the spiral we see today. But with streams stretching hundreds of thousands of light years, with ancient stars orbiting far beyond the bright disk, with remnants of collisions drifting like fossils in deep water, a different picture emerges. The Milky Way did not begin as a quiet structure. It began in violence. In the early universe, shortly after the first stars lit the darkness, small proto-galaxies collided endlessly. Each collision added mass. Each merger extended the boundaries. Each impact shaped the gravitational profile that still guides stars today. The size of the galaxy is not an accident. It is the lingering echo of ancient chaos. Far from the warm spiral arms, those echoes still vibrate through the halo. Stars older than the sun by billions of years drift in near isolation. They carry elemental fingerprints from a universe with far fewer heavy elements. Their existence proves that the Milky Way's outer regions began forming when the cosmos was young, dense, and filled with raw gas waiting to ignite into stars. These ancient halo stars are not arranged randomly. Their orbits reveal streams, loops, arcs, shells, signatures of past galaxies torn apart. Every one of those structures extends the Milky Way's reach. Every one shows that the outer boundaries were shaped long before the modern spiral formed. The size of the galaxy is therefore not a measure of its current state, but a measure of everything it has consumed. A galaxy of this scale also affects the fabric of the local universe. Its gravity creates tides stretching toward nearby galaxies. Its dark matter halo merges with the halo of Andromeda, forming a bridge of invisible mass connecting the two giants. This bridge is not theoretical, it is measurable. Stars and gas clouds drifting between the galaxies follow paths shaped by both gravitational wells. The region between them, once thought empty, is a dynamic zone of interaction. The size of the Milky Way also determines where its influence fades. At the outskirts, where the halo dissolves into the cosmic web, gravity grows thin. But even there, faint signatures remain. The galaxy leaves traces in the distribution of distant quasars. It bends, passing light in subtle arcs. It shapes the motions of tiny satellite galaxies, pulling them inward from vast distances. Some of these satellites orbit so far from the disk that their positions seem impossible under older models. Yet their existence fits perfectly into a galaxy twice as wide. Their orbits draw elegant ellipses through space, guided by the vast, unseen halo that envelops everything. Beyond satellites, rogue stars wander the outskirts. Some were flung outward by ancient interactions. Others drift from long-absorbed systems. A few may come from beyond the Milky Way entirely, passing through the halo like travelers crossing a borderless desert. Their presence adds weight. Their motion adds insight. Their existence adds depth. Each rogue star is a reminder that the boundary of the Milky Way is not a line but a transition. a long, slow fading from gravitational dominance to cosmic neutrality. The galaxy's true scale also reshapes the story of its future. A larger halo shortens the timescale for its meeting with Andromeda. The collision becomes not a distant event, but a gradual process already in motion. The earliest stages unfold in the unseen dark matter envelopes, where gravity has begun to merge the fates of both galaxies. What will one day become a majestic collision of stars and structure has already started silently, invisibly, in the spaces between. Even the sun's orbit gains new meaning. It travels through a gravitational field far larger than once known. Its slow path around the center takes it through regions influenced by forgotten collisions, past streams born in other galaxies, through tides that shift over millions of years. The solar system drifts through an environment shaped by billions of events, each one contributing to the vastness now revealed. The true size of the Milky Way is not just a measure of distance. It is a measure of history. A measure of everything that has shaped the galaxy and everything it will ever influence. It also reshapes the way humanity studies the universe. Because if the galaxy is larger, then distances to nearby objects change. Brightness corrections shift. Star counts increase. Chemical models adjust. Cosmic evolution becomes richer and more complex. The Milky Way becomes not a simple spiral, but a layered relic of cosmic time. Every measurement is recalibrated. Every calculation becomes deeper. Every answer leads to new questions. The size of the galaxy is not a number, it is a story. A story carved into light, motion, gravity, and darkness. A story that only grows more astonishing the farther humanity looks. A story demonstrating that the cosmos still holds more than any telescope has seen. As the understanding of the Milky Way expands, so too does the sense of wonder. The universe does not become smaller or more familiar. It becomes limitless again, as if every new discovery resets the horizon. A horizon that moves outward, forever widening. A horizon that defines both the galaxy and the human desire to know what lies beyond it. The true size of the Milky Way reshaped how scientists saw the galaxy's past and future, but it also changed something more profound, its place within the universe. For a long time, the cosmic neighborhood seemed simple. A small group of galaxies bound together in a structure called the local group. The Milky Way on one side, Andromeda on the other, and a scattering of dwarfs drifting between them like sparks around two great fires. But doubling the size of the Milky Way redefined that neighborhood. It changed the distances between structures. It changed the gravitational politics of the region. It shifted the balance of power in the darkness. Because the galaxy is not a city floating alone. It is part of a cluster of motion, a web of mass, a living network, shaped by forces extending across millions of light years. The local group once appeared small. Now it feels like a deep basin in the cosmic landscape, a valley in the fabric of space-time, shaped by two giants whose halos stretch toward each other, whose influence fills the sky even though the stars remain far apart. A larger Milky Way means its gravitational field reaches deeper into that valley. It means the region where the galaxy dominates is wider, more complex, more intertwined with the space around it. It means the Milky Way plays a larger role in guiding the motions of smaller galaxies. The dwarves that drift through the local group no longer appear as isolated wanderers. They are shaped by tides stretching across hundreds of thousands of light years. Some orbit the Milky Way. Some orbit Andromeda. Some move through the shared gravitational zone between them. Every path changed when the size doubled. Every orbit gained new context. Even the local group's long-term evolution shifted. For years, astronomers predicted that the Milky Way and Andromeda would collide, merge, and form a new elliptical system, nicknamed Milkdromeda. But the revised size changed the sequence of events. The collision does not begin when the visible disks touch. It begins when the halos overlap. And that stage has quietly started. The gravitational bridge already connects both galaxies. Invisible but powerful. A slow, ancient handshake across the void. As this connection strengthens, smaller galaxies begin to fall inward more efficiently. Their paths tighten. Their fates accelerate. The local group begins to collapse toward its center of mass, drawn inward by the combined pull of the two giants. But the Milky Way's expanded mass also influences something much larger, the structure of the cosmic web itself. Galaxies are not scattered randomly. They lie along filaments of dark matter stretching like arteries across the universe. These filaments feed galaxies with gas. They guide their motion. They shape their interactions. A heavyweight Milky Way pulls more strongly on its nearest filament. It bends the cosmic scaffolding around it. It alters the flow of intergalactic matter. The streams of gas entering the galaxy become stronger, denser, wider. They fuel new star formation, accelerate the birth of young stellar populations, and change how the spiral arms evolve. Even voids, the vast empty regions between filaments, shift subtly when a galaxy grows in mass. The borders of these voids warp. The distribution of matter becomes more uneven. The gravitational footprint of a larger Milky Way stretches far enough to alter the contours of cosmic geography. These are slow processes, measured not in years but in epochs. Yet their influence is real. The galaxy's true size links it intimately to the universe on the largest scales. Every boundary expanded by motion, every merger revealed by streams, every mass recalculated by gravity contributes to a picture where the Milky Way participates in shaping the universe around it. A galaxy is not just a collection of stars. It is a node in a cosmic network, a participant in a vast and ancient dance. The revised size of the Milky Way also changes how scientists interpret its environment. The local group is part of an even larger structure called the local sheet, a flat, thin region where galaxies align like islands on a calm ocean. Beyond that lies the Laniakea supercluster, a sprawling expanse of 100,000 galaxies bound loosely by gravity, all flowing toward the same gravitational sink. A Milky Way twice as large influences that flow more strongly. It becomes a more significant gravitational contributor within Laniakea's currents. It tugs harder on the surrounding structures. It shifts the balance of motion within its cosmic river. This conceptual expansion alters not only how the universe is mapped, but how humanity perceives its place inside it. The Earth feels smaller. The Sun feels quieter. Yet the very act of uncovering this truth makes human existence feel more profound, not less. Because a species living on a small planet orbiting an ordinary star buried inside a spiral arm of an enormous galaxy discovered all of this, measured it, mapped it, understood it. Not through guesses or myths, but through instruments aimed into the dark. By decoding the faint motions of stars thousands of light years away, by reading the subtle distortions of ancient light, by tracing invisible structures with mathematics and persistence, the galaxy's larger size does not diminish humanity's place. It elevates the achievement of understanding it. The Milky Way will continue to influence its surroundings for billions of years. Its gravitational field will guide the fate of nearby dwarfs. Its halo will merge with Andromeda's. Its structure will become part of a larger cosmic system formed in the far future. But for now, in this moment, humanity glimpses the truth of its home. A galaxy broader than expected, deeper than believed, more interconnected with the universe than once imagined. A galaxy whose story reaches beyond itself, touching every structure around it. A galaxy alive not only within its borders, but across the cosmic web that binds everything together. The Milky Way's expansion in size did more than reshape cosmic maps. It changed the way astronomers understand galactic identity itself. For centuries, a galaxy was defined by what could be seen. The stars, the arms, the glowing disk, the bright center. everything visible became the galaxy, and everything else dissolved into the dark. But doubling the Milky Way's measured size forced a deeper question. What is a galaxy, really? Is it the shining structure we see in photographs? Or the invisible halo that extends far beyond the stars? Is it the region where gravity dominates? Or the territory where its influence merely begins? The answer is not simple. It is layered, shifting, dependent on perspective. For an astronomer studying star formation, the galaxy ends where gas becomes too sparse to ignite new suns. For a cosmologist measuring dark matter, it ends wherever the halo fades into the cosmic background. For a dynamicist calculating orbits, it ends at the viral radius, the boundary where gravity can still bind an object. Multiple boundaries, multiple truths. All valid, all incomplete. The Milky Way challenges every definition. Because the galaxy does not stop, it transitions. It fades. It dissolves into a gradient of influence that stretches farther than light can reveal. Standing on Earth, humanity sees the Milky Way as a glowing band, a river of stars cutting through the night. But that glow is only the core. Only the bright center of an enormous system that extends much farther than the eye can grasp. Beyond the glowing disk, faint stars drift in the halo, too scattered to form constellations, too dim to influence the night sky. Beyond those stars, dark matter envelops everything. Invisible, silent, massive, the true skeleton of the galaxy. Every measurement technique, every map, every boundary drawn by human hands is merely an interpretation of a structure that refuses to be neatly contained. The expanded size also leads to another profound realization. The Milky Way is not a thing. It is a region, a gravitational landscape, a zone of influence shaped by both visible and invisible matter. When scientists recalculated the galaxy's mass, they discovered something remarkable. The distribution of matter is far from uniform. Dark matter clusters in uneven shapes. Stellar streams twist through the halo like ancient scars. Remnants of devoured galaxies swirl through the outer regions, their stars following orbits that seem to contradict symmetry itself. The Milky Way is not smooth. It is textured, layered, a palimpsest written over billions of years, erasing and rewriting itself through every merger. This complexity reveals a truth that textbooks rarely capture. Galaxies are not stable, polished objects. They are evolving ecosystems, shifting constantly under the forces of gravity and time. The doubled size exposes that dynamism. As the halo extends outward, its interaction with the cosmic environment becomes clearer. The edges blur into the intergalactic medium, a thin soup of atoms and radiation. Gas flows inward along filaments of dark matter. Winds blow outward from supernova explosions. Matter cycles between galaxy and void. What humanity once imagined as a clean boundary is actually a continuous exchange. A star ejected from the disk travels outward for millions of years. Does it stop being part of the Milky Way when it crosses the halo? When its orbit changes? When it is captured by another gravitational well? There is no single answer. A galaxy is not defined by walls, but by motion. The expanded Milky Way also reframes how scientists interpret cosmic isolation. For generations, Earth was viewed as a small world in a modest galaxy, far from cosmic capitals, a quiet suburb in a vast universe. But a galaxy twice as large, with more mass, more stars, more gravitational pull, is not modest. It is influential. It shapes the local cosmic terrain. Its halo competes with Andromeda's. It dictates the fates of dozens of smaller galaxies. It pulls on cosmic filaments that feed it. Humanity does not live in a small outpost. It lives in one of the great gravitational powers of the local universe, a giant hiding in plain sight. This realization also reframes the scale of the cosmic web. If the Milky Way is bigger, so are the structures it belongs to. Superclusters become more interconnected. Filaments grow thicker. Voids shrink. The universe becomes denser than once believed. Even the concept of a local group becomes fluid. The boundary shifts outward. The number of gravitational members changes. The paths of galaxies evolve under a different map than the one previously drawn. A larger Milky Way means the universe is not expanding into emptiness. It is expanding into a structure richer and more complex than imagined. Here is the most profound implication. Redefining the Milky Way redefines the universe. When the size of one galaxy changes, the mass of one galaxy changes. When the mass changes, the amounts of dark matter and dark energy inferred from cosmic models shift. When those values shift, the calculations describing the universe's expansion must be re-evaluated. A larger Milky Way forces scientists to revisit the foundations of cosmology. It is a reminder that knowledge depends on measurement, and measurement depends on perspective. Humanity measures the galaxy from inside it, a vantage point filled with limitations, blocked by dust, distorted by motion, obscured by darkness. The expanded size is not just a correction. It is a humbling acknowledgement that even the most familiar things in the cosmos, the place we call home, remain partially hidden from us. And perhaps that is the lesson the universe keeps repeating, that knowledge is not a destination, but a journey outward into the dark, a slow revealing of structures too vast to see all at once. The Milky Way is larger than believed, more massive, more complex, more mysterious. And even now the measurement is still changing, still refining, still challenging the limits of human understanding. Every discovery pushes the boundary a little farther. Every new instrument expands the map. Every observation adds another thread to the tapestry. The galaxy has no true edge, only the evolving horizon of what humanity is able to see. The Milky Way's expanded scale reshaped how scientists saw the galaxy's structure, but it also reshaped something even deeper, its timeline. Because a galaxy is not a static photograph. It is a living chronology of events stretching across billions of years, each layer built upon the last, each feature a remnant of something ancient. And doubling its size meant doubling the span of its memory. When astronomers remeasured the Milky Way, an important realization followed. A galaxy this large did not form quietly. It could not have simply grown through slow, gentle accumulation. Something far more violent shaped it. Its size told the story. A 200,000 light-year halo is not the footprint of a peaceful galaxy. It is the signature of ancient collisions, of deep gravitational wounds carved into the halo, of galaxies torn apart and their remnants still drifting through the outskirts. The Milky Way's past became sharper, not through new discoveries, but through the reinterpretation of old ones. When the boundaries expanded, so did the number of structures that belonged to the Milky Way. Streams once thought to be intergalactic became internal features. Dwarves once assumed distant became gravitational captives. Star clusters once labeled foreign became part of a single, enormous system. The galaxy's history became more crowded. One of the most dramatic insights comes from the realization that the Milky Way must have consumed dozens, perhaps hundreds, of smaller galaxies to reach its present mass. And in the far outer halo, the signatures of those meals still linger. Stellar streams loop across the sky like cosmic handwriting. Some are faint, thin as threads. Others are wide, stretching tens of thousands of light years. Each one is a fossil, the stretched remains of a galaxy that ventured too close, a testimony to a past encounter that ended in destruction. The expanded galactic radius recontextualized these streams. Their orbits only made sense if the galaxy was far larger than previously thought. Their distances only aligned with a gravitational potential that extended deeply into the dark. And so astronomers realized these streams were not decorating the edge of the galaxy. They were the edge. They were the markers of where the Milky Way's influence truly ended. The revision also altered the understanding of the galaxy's age profile. A larger galaxy implies a larger reservoir of ancient stars. Stars in the halo often date back 12 to 13 billion years, almost as old as the universe itself. Their chemical fingerprints reveal their origins. Their motions reveal the mergers that placed them there. By expanding the boundaries, astronomers found more of these ancient stars, lost in the faint outskirts. Their presence suggested a richer, more violent early epoch, a time when the Milky Way battled for territory in a young, crowded universe. Its size became a record of those ancient conflicts, a battlefield stretched across hundreds of thousands of light years. But the expanded size didn't just reshape the past. It widened the future. A galaxy twice as large evolves differently. Its gravitational pull lasts longer. Its interactions with neighboring galaxies begin sooner. Its path toward the inevitable collision with Andromeda becomes more intricate, more dynamic, more dramatic. A larger Milky Way means a larger first contact, not when the disks collide, but when the halos touch. And the halos, according to the new measurements, are already close to overlapping. This changes the entire predicted timeline. The future of the local group becomes a story already in motion. The outskirts of both galaxies are beginning to feel each other's pull. The frontier stars of each system now orbit inside a combined gravitational landscape. The collision, the great merger of galaxies, no longer belongs to the distant future. Its earliest stages may already be unfolding quietly in the darkness between stars. But even beyond the Andromeda encounter, the Milky Way's expanded size changes the final chapters of its cosmic life. Every galaxy eventually faces decline. Gas is used up. Star formation slows. The luminous spiral arms fade into red populations of ancient suns. After the collision with Andromeda, the newly formed elliptical galaxy will settle into a long, slow twilight. But the path to that twilight becomes more complex in a larger system. A bigger halo means more satellite galaxies are captured. More material is available for star formation after the merger. More tidal tails form and fall back, feeding the newly merged core with gas. The galaxy's end becomes richer, more prolonged, more dramatic. The larger size also reshapes the question of cosmic isolation in the far future. As dark energy drives the expansion of the universe, galaxies beyond the local group will drift away faster than light can cross the void. Eventually, only the merged Milky Way-Andromeda system will remain visible. Everything else will fade beyond the cosmic horizon. In that isolated future, a larger Milky Way today means a larger cosmic island tomorrow. More stars, more remnants of ancient collisions, more traces of the universe's early structure, preserved long after everything else becomes unreachable. In a sense, the galaxy's expanded size is a gift to distant descendants, a richer archive of the universe, left behind when the cosmos becomes cold, dark, and empty. But there is one more profound implication. The newfound size forced astronomers to realize that the Milky Way is not unique in its complexity. Every galaxy may be more intricate than believed. If one measurement was wrong, many must be. And so the Milky Way becomes a template, a mirror held up to the rest of the universe. Its doubled radius pushes scientists to re-examine every spiral galaxy, to reconsider mass estimates, to redraw maps of cosmic evolution. The Milky Way is not just a larger galaxy. It is a larger question, a reminder that even the structures we thought we understood remain partly concealed by darkness. A reminder that the universe still holds its secrets close, revealing them only when humanity builds instruments powerful enough and asks questions deep enough to uncover the next layer of truth. A reminder that the story of the galaxy, like the universe itself, is always bigger than it seems.